This conference will now be recorded.
Trying to get this. This happens all the time. Start the recording and then I don't know how to get the recording thing off. Okay, there we go. That's good. All right. So first thing in chapter 15. You've got some background noise there. Do you know what that is?
No.
Okay. So I'll just ask you to mute, and then if you have a question, unmute and ask me. That's all. So 15.1 is it's called the analysis of the residuals. And it basically, if you recall, anytime we did a hypothesis test, there's certain assumptions have to be met before we can actually perform that hypothesis test. So the analysis of the residuals, which is what this is called, helps us determine if we're going to meet the assumptions necessary so that this particular set of sample data can be used to perform a hypothesis test and to make interpretations about the actual population of data. So that's the idea here. This analysis of residuals really looks at our error values. And we did this a little bit at the beginning of chapter 14, where we found e-values and we did the line of best fit. But this time we're going to look at the e-values, and all your errors are your y sub i's minus your y sub hat. So what this means is the y sub I is your raw data from the sample. Okay. Your y sub hat is the value you would get by plugging x into the regression equation. So if you plug x into your regression equation, you get y hat, but y sub I is the actual raw data. The idea behind this is that suppose, because we're talking about Corvettes here and the age of the Corvette and the price. So suppose we have a 6-year-old Corvette. Well, there's hundreds of thousands of 6-year-old Corvettes out there in the world. Well, if we plug it into our regression equation, we're going to get one value for what the value of that Corvette should be. But in reality, in the real world, all 6-year-old Corvettes are slightly different from that. And the idea is that all 6-year-old Corvettes, their value will be normally distributed. And then all 5-year-old Corvettes, their value would be normally distributed, and so on and so on. So the way we can kind of test this with our sample is doing what we call a residual plot. And a residual plot is something you are going to have to do on the test. So it's going to be one of those things you're going to have to do on the scrap paper, and I'm going to have to look at it when you upload it. And the way a residual plot works is first, in order to do it, you have to actually get all your y hat values. So what I'm going to do is move our regression equation over for a minute so I can have some space under my graph. I'm going to erase this space right here. Okay, and I'm going to extend my graph now, my table, because the first thing I want to find is what are the predicted values. So in other words, if I plug the x value of 6 into my regression equation, what is the value I'm going to get? So that's the first thing we're going to do. And I had done these, but so I'm gonna go ahead and put them in. But you can, as I'm working on, you can try a couple just to make sure you're getting them right and make sure I have them right. So what you want to do is figure out, okay, what if x equaled 6? Then you'd have y hat equals 456 point. That was a 9, by the way, not a 6. Sorry about that. 0.59 minus 27.9 times 6. Okay, so I want you to go ahead and calculate that and then do the same thing for a 2, a 5, a 4, and a 1. You're not going to be able to get to all of them, but I'm going to plug in the numbers I got. And if you could randomly check some of them to make sure you're getting the same thing, that would be great. So for 6, I got 289.19. For the 2 2s, I can't write it like all the times because it's well, let me see if I can make this bigger. That might work better if I make it a little bit bigger. Then I can get the numbers in there. Yeah. So I got 289. So for 6 again, 289.19, and for 6 again, 289.19. And then for the 2, I got 400.79. For the 5, looks like I got 317.09. And this is 5 also. Whoops. For 4, I got 344.99. And for 1, I got 428.69.
I got all those values too.
Oh, good. Okay, so we're good there. I'm going to shrink this up then. If anybody is doing this at home, they can take the time, jot those numbers down, but I'm going to make this smaller now. Well, not too much smaller because we've got to do the E values. So as I had stated, your error value is going to be each y sub I minus y hat. So that means you're going to take the raw value of 290 and you're going to subtract y sub hat. So I have not done that yet. So we need to go through and do that, and then we can just double check our numbers real quick. So take a moment if you don't mind. And you're going to subtract. So you'd start with 290 minus 289.19. And then you got to do it for each one because the raw value is different now. 280 minus 289.19. And you want to put the, make sure the sign is there, the negative or positive. And this is why it's also really important that you take the raw data minus the predicted y hat. If not, your graph will kind of be the opposite of what it should be. So stop me if you get a number that's different than any of these.
I'm confused on why you're doing it for like why it's different for each 6.
Because the raw data is different. So this 6 was the value was 290, but this 6 the value was only 280.
Okay.
Yeah, it would be 290 minus that 289, but this one's 280 minus that. Yeah.
Oh, I see. Okay.
Yeah, so each piece of raw data is going to have a different E value.
Okay. Thank you.
Mm-hmm. Like I said, I'll give you a second, just see if you can verify a few of them. I think they should be good. 5, 3, 4, 25, 28, 20, 17.
Yeah, I got those.
Yeah, I was just looking through my calculator. They look good. Okay, so the way a residual plot works, it's a mini, I gotta shrink them up a little bit. It's a mini graph that you make. So you wanna draw kind of a part of a box. But the way the graph is going to work is your X values are gonna go across the X axis. So that part makes sense. So if we look at our X values, they go from 1 through 6. So we just need a 1, 2, 3, 4, 5, 6. Now we're going to kind of move our Y, our X, our 0, and we're going to put the 0 line here. Because we're not going to graph any of the Y values, we're going to graph the E values, and we're going to graph them from this 0 line. So what that means is for our E values, you got to kind of look at the highest positive value and the smallest negative value. And it looks like, what do we have? We have a -19, but we had a 24. Okay. See how the highest one is like a 24? The number that's further away from 0 is 24. Let me move something for a minute so I can erase that out of the way for a second. So because our number that's furthest away is 24, you're going to, on your y-axis, put, oops, sorry, I erased mine by accident. There we go, get it back. You're going to put the 24 up here and kind of break it up. So that would be 12, 6, 18. And you're going to break it up the same way here with the negatives. You kind of need to quickly come up with some scale that makes sense. And it's really going to be based off of which value is the furthest away from 0. And because 24 was the furthest away from 0, I just did it that way. You can do it by 5s, you can do it by 10s, you can do it any way you want. Just keep it consistent with the positives and the negatives. So hopefully that makes some sense. Like if I wanted to, I could have done 10, 20, 30, -10, -20, -30. I could have gone that way. That would have been fine too. I kind of just picked this, but you can pick anything you want for your scale. Once you get a scale, you are going to plot these E values. So if we take a look at the 1-year-old, go to the 1. The 1 has 1 E value and it's -3.69. So if that's -6, -3.69 is going to be a, whoops, I just put that at 2. Sorry. -3.69 is going to be about right there. And there are no other values at the 1. But at 2, we have 2 different E values. Take a look at your 2. One E value is all the way up here at 24. And the other E value is down at -16. So there's -18, so -16. And remember, this is just a rough plot. And you continue that process. There are no values at 3 because we don't have anything in our data that's 3 years old. At 4, we have 2 of them. We have a 10 and it's approximately -20. So at 4, I've got one that's at around 10. Sorry, I'm looking at my thing on a slant and I'm making the numbers really far off. So I've got one at a 10 and one down at a -19. And then for 5, I also have 2. I've got a -2 And for 5, I have another about 10.9. And for 6, I've got quite a few of them. I've got one at 0.18, so that's just right at the line, slightly above it. I got -9. That would be about there. And I have one at 5, which is about there. Okay. So I'll kind of let you look at that and make sure you understand how that gets graphed. But that is technically simply called a residual plot. It's a plot of the e-values. And once you have yours done, we can kind of take a look at what this plot means. I'm just going to shrink it up a little bit.
I finished.
Okay. So what we're looking for, and this is really just an estimation, but you're looking for your values to be pretty evenly dispersed in a horizontal band across above the 0 line and below the 0 line. So when I say that, I mean, okay, our values are like here, here, that's pretty good. They're just in this nice little horizontal line, kind of a horizontal band. To understand what I'm talking about, it's easier for me to just draw a few that would not meet the assumptions. And this horizontal band I'm talking about tells us things that we have a normally distributed population with equal standard deviations, and it tells us we've met our assumptions to move forward with a hypothesis test, to use our sample to make inferences about the entire population. But let me show you what one that would not meet assumptions look like, because it's kind of easier to see that. So here's a little one. Suppose I had one that looked like this. Okay. So do you see the difference? See how in the one we did, there's kind of equal amount, it's going above and below. But do you see in this one we have below, then we have everything above, and then we have everything below? This one would not meet assumptions because it's kind of not a, I'm trying to come up with the right, they call it a horizontal band that moves across. It's symmetric. Think of horizontally symmetric. So this one is horizontally symmetric. We would say yes, meets assumptions. This would be an example of not meeting assumptions. Another example would look like this. Suppose our data starts off really closely clustered and then all of a sudden gets really far away. That does not meet assumptions. Oops. So again, you're looking for a nice horizontal band. You can say it meets assumptions. If you have a clear like in either of these two examples, where it's not a nice even horizontal band, then you would have to say it does not meet assumptions. And those assumptions I'll go over in detail when I put the video out, but it just has to be like, okay, we have equal standard deviations, we have normal, the data around each year is normally distributed and stuff like that. That's everything from 15.1. So for an example from 15.1 is just, you're gonna make a residual plot for me with a set of data. Okay. If you're good with that, we will look at the different hypothesis tests that we are going to do related to this material. And just let me know if you're ready to move on, because I'll need to erase what I did to do the next section.
I'm ready.
Okay, so let me get rid of 15.1. I know there's probably an easier way to do this, but oh, yeah, large eraser. Let's try that. It's not much larger. Okay, so the next two sections. So in our book, we're going to do 15.2 and 15.4. I am skipping 15.3. It's not really needed, and we're coming to the end of the semester, so that's all in the document that I'm going to put out to the class later today. But 15.2 has to do with inferences for the slope of the population regression line. Inferences for the slope of the population regression line. And the idea here is, and this is the question that you will be asked. It will be at the, let's do 5% significance level. Do the data provide sufficient evidence that the age of a Corvette is useful as a linear predictor for its price? Sorry, it's sloppy. So at the 5% significance level, do the data provide sufficient evidence that the age of a Corvette is useful as a linear predictor for its price? I'm also going to get rid of this. We don't need these anymore. So here we have this set of data. We were able to make a regression line for it. We got some information from the regression line based off the coefficient of determination. But now we're going to say, hey, you know, does this data, does this sample give us enough evidence to say, yes, we can use the price, the age of a Corvette to predict its price. It's useful in predicting the price. And there are two different ways we can kind of look at the usefulness. The first one is 15.2, which is based off the slope. So the slope we have here in our regression line is negative 27.9. The sample slope that we refer to as B sub 1, right? That is our sample slope. Whoops. From our regression line is negative 27.9. But we're talking about slope in a more general sense, such as a population. When we talk about population slope, we use capital B, B sub 1. So again, it's very similar to other things we've done in here. The lowercase is the sample. In this case, the uppercase B represents the population slope. So here's the idea. if our slope were actually equal to 0, so we're going to do a null hypothesis that says our slope equals 0, what that means, it is not useful. Because a 0 slope's a perfectly horizontal linear line, and I talked about this in one of the earlier videos from chapter 14. If we have a 0 slope, then that means your x value is really not predicting your y value. So 0 slope means it's not useful. So we start with the assumption there's a 0 slope. Then we're going to see if there is enough evidence in our data to say that our slope is not 0. It does not matter negative or positive. You're never going to be less than 0 or greater than 0. This is the only hypothesis, an alternate hypothesis, that you're going to use for usefulness. This tells us our regression line that it is useful. Okay. And if you kind of take a look at your formula sheet for a second, and I don't have them on here. So I'm going to pull up real quick. I don't think I have the full formula sheet, do I? No. All right. I meant to put the formula sheet on there. Do you have your formula sheet in front of you by any chance?
I do.
Okay, good, because it'll take me too long to log into Canvas right now to pull it up. I meant to put chapter 15 underneath it here, but I didn't do that yet. If you kind of take a look at usefulness, I think it does have it lists for you, beginning of chapter 15, H sub O, B sub 1 equals 0. I think that's,
Yes.
yeah. So anytime you hear usefulness, this is what you're using. So the formula, it's a t-value formula. I believe the formula is, we're obviously going to start with our regression, our sample slope of b sub 1. Then it has this new value s sub b.
Yep.
And it's divided by the square root of s of x. Correct?
Yep. Correct.
Good. So the new value is this s sub b value. We've already worked with b sub 1. You know that's the slope from the regression line. S sub xx, we actually did find, that's something that you'll either be given or you found already, that S of xx value. The S sub b is a new one, but the formula should be there on your formula sheet, and it is the square root of S of EE over n minus 2, correct?
It is
SSD, yeah, over, I think,
SSD.
2. Is that right?
Yep.
Just,
Yeah.
okay. This is the standard error of the estimate. So basically, it's the standard deviation of all your e-values. So at the end of the day, that's all that is. It's your standard deviation. Okay. So again, very similar to what you're used to. The standard deviation has a new name now. It's the standard error of the estimate. So it's standard error of all those e-values we had find. So we basically have everything we need right now to calculate our test statistic. So a lot of this information I took from what we did in last week's office hours when we worked out all this with the Corvette problem. So you're not going to have to find all this for each new problem. It'll already be given to you, or it'll be from a previous problem you worked on. So your B sub 1 is negative 27.9. Okay, let's find S sub E. S sub E is the SS standard, the sum of the squares of the error, which we calculated last week, and that was 1623.71. Or actually, last week, we calculated the sum of the squares of the regression and the sum of the squares of the total, because we needed to do that to find our coefficient of determination. But because the regression identity is SSR plus SSE equals SST, you can easily get SSE by subtracting those two values. And then of course n minus 2, and what do we have here? 1, 2, 3, 4, 5, 6, 7, 10. So divide it by 8. So go ahead and calculate that so we can get that value. Let me do it as well. $14.25.
Yep.
Okay, so our SSE is 14.25, and then you put that over the square root of S sub XX, which again, that was calculated last week. So we have that, and that was 30.9. And use those values to get, 1 second, square root. I got negative 10.88.
Yeah, that's what I got.
Okay. Once you get your test statistic, everything is like everything else we've done with hypothesis tests so far. It's just a T. Oops, I didn't make that small. It's a T value, so you can use either your critical value or your p-value approach. We can just go ahead and use the critical value approach. Either one's going to be exactly the same. So if we use that critical value approach, we need to look up the degrees of freedom. And just check your, I'm pretty certain degrees of freedom should be n minus 2. So your degrees of freedom should be 8.
Yeah, it's on -2.
Yeah. So you want to go to a T table, which I don't have in front of me actually. So if you can pull up your, oh, no, I do have it in the book here. That's right. So go to a T table. We did the 5% significance level. So to get a critical value, we're just going to look up T.05 at 8 degrees of freedom. So we want at 8 degrees of freedom. This is for the critical value approach.
I got 1.860.
1.860. Sorry, I was so used to doing ANOVA and chi-square tables, I was drawing the wrong curve for a second. Okay, so the other thing we want to remember is, and this we kind of, yeah, it's a two-tailed test, right? It's definitely a two-tailed test. So we're not looking at 0.05, right? That was my mistake. Because it's a two-tailed test and all of our slope hypothesis tests are two-tailed, it's not 0.05 we want. Because it's two-tailed, it's actually 0.025 because we got to split that 0.05 into 2 sections. This isn't anything we had to do when we were doing with chi-square and ANOVA because they were always one-tailed test. So my mistake, it's not going to be the 1.860. It looks like it's going to be the 2.306. So we got to use, again, the two-tailed test because we're doing a not equal to. And all slope hypothesis tests are going to be two-tailed. So your 0.05 needs to be split into 0.025 and 0.025. So we're going to use 2.306. Either way, it didn't matter because -10 is clearly way out here, and it is in our rejection region. And what's nice is this will be consistent with information you got for things like the coefficient of determination, which also we had a pretty high coefficient of determination in this problem, which told us that yes, our graph was going to be useful. So it makes sense that we end up rejecting the null hypothesis that it's not useful. And we can say, yes, at the 5% significance level, the data do provide sufficient evidence to conclude that the age of a Corvette is certainly useful in predicting its price. So just let me know if that makes sense, and then we'll move on to the other one, which is very similar.
It makes sense.
Okay. Yeah, and that's one of the things, that's what's nice if I give you kind of one problem and you go through all the steps with that one set of data, because if you have a high coefficient of determination, you're going to very likely reject this because they're all kind of tied together with this particular set of data. The other way to test on how related the X value, in this case, the age of the car, and the Y value, the price of the car, is through correlation. So we're going to skip over to 15.4. For a second. Just erase this. And this is going to change as well. So 15.4 and 15.2 are similar in that they are ways to letting us know how useful price is in predicting the age of the car. They just do it slightly different. So 15, like I said, I'm skipping 15.3. It really is not relevant enough for this to do it this semester. But 15.4 is all about correlation. So this is inferences in correlation. And what we're looking at, we're kind of forgetting the regression line for a minute, and we're going to look at just these two variables. Are they correlated with each other? That's what we're looking at in 15.4. But yes, it is another way to determine how useful one is in predicting the other. But we're kind of just changing the way we think about it a little bit. So the equation changes a little bit. Let me get that for you. So this would be at the 5% significance level. Sorry, that was really sloppy. I really look forward to the day where I can write on the board again and not on these computer tablets. So this time it would say, do the data provide sufficient evidence again? To conclude that age and price are negatively linearly correlated. So question I usually get at the end of chapter 15 is, well, how do we know which hypothesis test to use? If the hypothesis test has the word correlate in it, you're using this one. If the hypothesis test talks about usefulness, you use the slope one. Okay, this time we're talking about correlation. Now, to do correlation, we need to introduce, you know, R. R is our correlation coefficient that we found in last week's session. And we got it to be negative 0.97, which told us, hey, this sample was pretty closely linearly correlated. So we should again be able to reject here, of course. But R is for the sample. For the population, we introduce a new variable called rho, and it kind of looks like a fancy P. And that is our population correlation. So R is the point estimate for the population linear coefficient of rho. It's not a P, it looks like a P, but it's definitely not a P, it's the Greek letter rho. So that's the population correlation coefficient, where R is the sample correlation coefficient, okay? So the same idea exists here. When we talk about correlation, if our two variables are completely uncorrelated, it equals 0. That means uncorrelated. Absolutely no correlation at all. Now, unlike slope, correlation can go in either direction. It could be negative, in which case rho is less than 0. It could be positive, in which case rho would be greater than 0. Or if you are not given a direction of negative or positive, you would just say rho does not equal 0. Okay? In this particular problem, we are asked for negative linear correlation. So we're going to have rho less than 0. That means a negative correlation. And that's what we're checking to see. Now, this formula is much simpler. You can kind of take a look at it on your formula sheet. It's still a t-test, but it only uses one variable, the sample correlation coefficient. So it's R over the square root n minus 2. So we only need that one variable, which is the sample correlation coefficient, which we found last week to be negative 0.97. So you can go ahead and plug in that negative 0.97. Be careful with the negative signs here and use parentheses carefully, because the negative 0.97 does get squared and does become positive, but it's still 1 minus that. So far I have negative 0.97 over square root, and I get 1 minus 0.9409 over 8, because 10, and then it's 10. That's negative 0.97 over 0.0591 divided by that 8 is the square root 0.0074. Take the square root of that. So I got negative 0.97 over 0.85. 595. There's another, it was 0.08, sorry. And it looks like I'm getting a negative 11.29 about. And you could be off a little bit depending on where you rounded and how you plug the numbers in, but check that and see if you got somewhere around that.
I got that.
Okay. And the test statistic, it's actually going to be very similar to the one with slope because it's the same set of data. And again, if we run so this one we can even do a p-value approach if you wanted to. If you did a p-value approach, okay, this one is a left-tailed test. For a p-value approach, you would put the negative 11.29 here. You would look at your t-table. We're still at 8 degrees of freedom. Clearly, negative 11 is nowhere on that t-table. It's way off the chart, which kind of tells us that our p-value is less than 0.005. And since p is smaller than 0.005 and alpha equals 0.05, p is smaller than alpha and we would reject. Now, both of these tests can be completed in a graphing calculator. What you would have to do is put the list of data into your lists on the calculator, like put L1 as your X's, L2 as your Y's. And then when you go to tests, there's something called a linear regression t-test, and it will actually do both the B and the row for you. So you have to select though for the row whether you're doing a not equal to, a less than 0, or greater than 0. And these can be done, you can get exact p-values from your calculator. And again, we would say, of course, at the 5% significance level, since we're rejecting the null, we say the data do provide sufficient evidence to conclude that the age and the price of Corvettes are negatively linearly correlated, meaning as the age goes up, the price goes down. So I'm going to stop this recording here because this kind of goes over the completion of what we did last week.